Good afternoon. Welcome to the final week of this NPTEL course on applied optics. This is our last session. We will definitely have one more review session where we will revise the concepts learned in this entire course. But officially today is the last week of the course, so this is the last session, last live problem solving session. In this week there were quite a lot of topics which were discussed. For example, anti-reflection coatings, lasers, optical fibers, and holography. So, wide variety of topics which were covered in this last week. So, the assignment problems also for this week are regarding lasers and optical fibers. Once again, before proceeding, let me put the link to the YouTube channel in the Zoom chat box. So if you have missed any one of the previous sessions, you could watch the recording of the YouTube of this live problem solving session on the YouTube channel. We will have the last class next Saturday, which would be a review class wherein we will just revise the concepts learned over this 12-week course. So let us get started with the first question. The angle of refraction of a light ray launched at critical angle would be what we need to select. So this is a simple question on critical angle. Let me launch the poll for all of you. All the students, please select the correct answer to this question in the poll, in the Zoom poll. I have seen sometimes people write the correct answer in the Zoom chat box. Please refrain from doing that. Select the correct option in the poll itself. Take about a few minutes to answer this, and then we will discuss the answer. Okay, so let us now discuss the answer. This question is based on Snell's law. So let us say we have an interface of refractive indices n1 and n2. We have a ray which is incident in the denser medium and then goes to the rarer medium. So we have this ray incident on the denser medium and then it refracts into the rarer medium. Here is the normal. Now this is my angle theta I and this is my angle theta r. But what if we increase the angle theta I? So if I increase it slightly, then at one particular angle of theta I, we will see that the refracted ray goes parallel to the interface. And if we increase it further, then we will see that there is no refraction. Instead, the beam is reflected in the same medium. So this particular angle is called theta c, which is critical angle. Sorry. It is the angle at which the refracted ray goes at 90 degrees. So this is 90 degrees. Now, if we discuss in Snell's law, then according to Snell's law, we have n1 sine theta I equals n2 sine theta r. And we want to see the case for which theta r is 90 degrees. And note that this will happen only for this case wherein, this is, I wrote reverse, n2 is less than n1. From denser to rarer I am going. So this is denser medium and this is rarer medium. So this case will happen only when we move from a denser medium to a rarer medium. So at critical angle, the refraction angle is 90 degrees. And this is my critical angle, the angle of incidence for which this happens. Now, if theta I is less than theta c, then we see refraction, this purple line. This is the purple ray. If theta I equals theta c, then this is the case of critical angle, and in this case the refraction angle is 90 degrees. This is the pink ray And when theta I is greater than theta c, then we see the case of total internal reflection. Meaning there is no refraction. The ray is reflected back within the same medium. This is the case of the red ray. So this is the concept of critical angle and total internal reflection. That means the correct option for this question is option C, 90 degrees. Okay, so moving forward. Question 2. The phenomenon responsible for light guiding inside the optical fiber is what? We have 4 options. I will restart and relaunch the poll. Please take a few minutes to answer. Okay, so the correct option is total internal reflection. And we just discussed this effect, total internal reflection, in the above question. And the application of it is in the usage of optical fibers. So we have this optical fiber, and refractive index of the medium inside would be n1, outside n2. And let us say that there's a light ray which is entering the optical fiber, then it will get reflected at the walls of the fiber, and this reflection is nothing but total internal reflection. So if I draw the normal, so if this is theta I, this is also theta I from the laws of reflection, and this theta I has to be greater than theta C, then we are in the regime of total internal reflection. And let's say the refractive index of this medium is n1, this medium is n2, and this medium over here also is n2, then theta C is sine inverse n1 over n2. So the correct option is total internal reflection, option B. Let me check if there are some questions in the Zoom chat box. Sorry. Okay, so there seems to be no question. So if at any point of time you have any question, feel free to unmute yourself and ask, or you could put it up in the Zoom chat box as well. Okay, someone is saying that I am not audible. Is that the case? Can someone else write in the chat box whether they are able to hear or not, or give a thumbs up if I am audible? Okay, let me check the YouTube stream. So if someone is facing problems in network or audio or some such thing, then I would suggest heading over to the YouTube channel and watching the stream over there. Sometimes Zoom does funny things, and as a result you don't see or hear things properly, but in YouTube I have seen that the stream works perfectly fine. Or else you could just rejoin this meeting. I guess that should fix it. Okay, so moving ahead. Refractive index of core and cladding of a fiber are 1.4565 and 1.45 respectively. The numerical aperture of the fiber would be option A 0.13. This is a simple numerical question. So this is another question on optical fibers. This one is a simple numerical question based on optical fibers. And I have restarted the poll for all of you. Please do answer the poll. Okay, let us now discuss the answer. So let us say we have core. So this is my optical fiber. It consists of a core and a cladding. Sorry. This is the cladding. A cladding is like a covering for the core. It prevents the loss of the field into air. So this is my core. This is my cladding. And this is N0. This is N1 greater than N0. This is N2 greater than N1. And this again is N0. And this is N1. Now let us consider a ray incident on this fiber. So this is the entrance to the fiber. This is my incident ray. This is how it goes, and then total internal reflection, and this is how the ray is guided. Let us draw normals. So this normal here and one normal here. So this angle, let us call it I, and this angle, let us call it theta, and this angle is phi. This angle due to total internal reflection is also phi. Again, we will make use of Snell's law. So by Snell's law, we have N0 sine I equals N2 sine theta. This is for the entrance to the fiber, and this is equal to N2 cos phi. Why? Because phi is 90 degrees minus theta. Now for total internal reflection at the core cladding interface, for total internal reflection. We need to have phi greater than theta c, and theta c is nothing but sine inverse n1 over n2. Sorry, here I had written wrong. This was n2 over n1. It is the second surface over the first surface. So refractive index of the second surface over the refractive index of the second medium over the first medium. This means that sine phi should be greater than n1 over n2. So sine squared phi should be greater than n1 over n2 squared, which means 1 minus sine squared phi should be less than 1 minus n1 over n2 squared. When you multiply with the minus sign, the sign of the greater than or less than changes. And 1 minus sine squared phi is nothing but cos squared phi, so that means cos squared phi should be less than 1 minus n1 over n2 squared. So now coming back to this equation, and then plugging in this, now if n0 is air, that is if this medium is air, so n0 is 1 in that case, then we have sine I is less than square root n2 squared minus n1 squared, and this term on the right hand side is what is known as numerical aperture. And this basically determines the range of incident angles. Because I is the incident angle entering into the fiber, so this incident angle should satisfy this inequality. So this means I should be less than sine inverse square root of n2 squared minus n1 squared. So that means the maximum value that I can take is sine inverse n2 squared minus n1 squared, and the minimum is of course 0. So I belongs to so this is the range of values for I, the incident angle. Now we can just plug in the values. So NA is square root n2 squared minus n1 squared, and n2 we are given is the value for the core, minus n1 squared the value for the cladding, let me pull out my calculator to find this out. Okay, plugging into the calculator gives approximately 0.1374, which is approximately 0.14, but there's no such option. The options are somewhat incorrect, but the closest option would be option A, 0.13. So whenever we round off, we don't just terminate. So if I want to round off at the second decimal place, I will not just terminate. I need to look at the number next to where I want to round off. So if I want to round off to 2 decimal places, then I need to look at the value of the third decimal place. If that value is greater than 5, then I will round to a number higher, and if it is less than 5, then round to a number lower. So for example, had it been 0.1334, then this would be 0.13, round off to 2 decimal places. But 0.137 4, we look at this number 7, it is greater than 5, so that means I will move 3 to 4, so rounding off would give me 0.14. Moving over to the next question. Each wavelength takes different amount of time to propagate along the same path. This phenomenon is called A. Polarization inversion, B. Dispersion, C. Power loss, or D. Stimulated emission. Very simple question. Please take about a minute to answer. Let us now discuss the answer. The correct option is option B, dispersion. I don't even understand what is option A. Polarization inversion doesn't really make any sense. Stimulated emission is used for lasers, and power loss is, as the name suggests, it's just loss, meaning the field getting absorbed in some medium that leads to loss. And why this happens, why does different wavelength take different amounts of time, uh, essentially why does dispersion happen? This is because the speed of light in any medium is governed by the refractive index of that medium, and refractive index is not a constant, it is a function of wavelength. It depends on wavelength, and it is approximately given as follows. A very simple model for refractive index as a function of wavelength, and this model is known as the Cauchy equation. And you can see that refractive index is inversely proportional to wavelength. So longer the wavelength, smaller would be the refractive index, and smaller the refractive index, meaning higher would the speed be. So for different wavelengths we have different refractive indices, which leads to different speeds, and different speeds meaning the wavelength will take different wavelengths will take different amounts of time to travel the same distance. Let us proceed further. The fifth question: population inversion oh I see, this could be over here in this if this was this population inversion, then the option made sense, but even after that it would not be the correct option. So population inversion is not possible in which of the following cases? Let me refresh and restart the poll. Okay, there you go. Please take a few minutes to answer. The correct option is option A, two level system. Oh, sorry, let me change the color of my pen. You cannot achieve population inversion in a two level system. So, you cannot have a laser having two level system. And let me draw a two level system. So the energy for this level is, let's say, E1. For the higher energy it is E2, which is greater than E1, and there will be some atoms N1 in the E1 state, some atoms N2 in the E2 state, and then we have Boltzmann's law. According to which the ratio of N1 and N2 is as follows. Which is nothing but e to the power h cross omega over kbt. Now, from this we can easily see what happens as a function of temperature. So if temperature is very small, then we see that N1 is very large, and if temperature becomes very high, if we increase the temperature slowly, then we see that N2 slowly increases in comparison to N1, and N1 decreases in comparison to N2, and we reach the case where N1 is nearly equal to N2, but we can never get N2 greater than N1. We can never get the case where N2 will be greater than N1, and we need N2 greater than N1 for population inversion and for laser action to start. So in a 2-level system, this is not possible. It is possible in 3-level system and in 4-level systems. The next few questions are very factual questions. There's nothing really to solve. It's just facts based on lasers. So it's either you know them or you don't know them, these facts. So let me write down. We are halfway through, 5 questions done, 5 more to go. Every week, as you would be knowing, we solve 10 questions from the previous year's assignments. So question 6. So very factual question. We are asked in which particular laser do we use xenon or krypton flash lamps for pumping. So please take about a minute to answer. So the correct answer is ruby laser. And what do we mean by pumping? So pumping means to pump atoms or to send atoms to higher energy level to create the situation of population inversion. And this is done when atoms absorb energy from the lower energy level uh, and then they go to the higher energy level, and only when the situation of population inversion is achieved will we see the lasing action. And ruby laser works on the concept of a 4-level system. Next question is also on ruby laser. The output wavelength of the ruby laser is what? Another factual question, so please take a minute to answer the poll. Sorry. The correct answer to this is option A, 6943 angstroms, and this is essentially red laser. Next question. Lasing action starts when? Again, a very factual question. In fact, something which we have been discussing all throughout in this assignment. So now you have to just select the correct option. Sorry. The correct option, as many of you rightly selected, although I'm still waiting for that one question which everyone gets right. So that's still a dream for me. But nevertheless, most of you got this one right. The correct option is leasing starts when population inversion is achieved. And this population inversion is required for amplification in the laser. Next question, we have just 2 more questions to go. This is on anti-reflecting coatings. So this is a simple numerical question. take about a few minutes to answer. Let us now discuss the correct answer. Let's say we have this glass slab. This is my glass slab, and I want to have an anti-reflecting coating on top of it. This is my anti-reflecting coating. So refractive index of glass is Ng, refractive index of coating, let that be Nf. Now for this to be anti-reflecting, what happens is, let's say there is one incident ray and it reflects from the top surface of the coating. Then let us say there's another ray, choose some other color. Let's say there's another ray which gets reflected from the glass. So we have these two rays. Now we will observe no reflection, or what is called anti-reflecting coating, meaning there will be no reflection. For the case when there is destructive interference, between the red and the pink rays. And this destructive interference will lead to the case of no reflection. So only transmission. And for destructive interference, we need to have path difference of lambda by 2, half a wavelength. Now path difference is this extra path traveled in the film, and let us call the thickness of the film to be d. So path difference is this green path, and that is twice of Nf times d. Nf is the refractive index and d is the thickness of the film. Why Nf times d? Because d is the geometric path and NFD will be the corresponding optical path. So 2NFT equals lambda over 2. This gives me D equals lambda over 4 times NF. Plugging in the values now. Lambda is 500 nanometers. NF is 1.38. Note that the refractive index of the glass is redundant information over here. So plugging in these values in my calculator gives me roughly 90.58 nanometers, which is approximately 90.6 nanometers. Option A is the correct option. Note that this particular value of thickness for this particular anti-reflecting coating will lead to destructive interference for the particular value of wavelength 500 nanometers. If we deviate from this wavelength, then we will observe some amount of reflection as well. So anti-reflection coatings work best for a single wavelength and maybe some narrow bandwidth around that wavelength. But if we deviate too much from that wavelength, then we will see significant amount of reflection. So this anti-reflection coating is basically an application of interference. Destructive interference to be specific. Finally, the last question. This question is on hologram. Again, a very factual question. A hologram records what? Very simple factual question. Take about a minute to answer. I will restart the poll for one last time. Okay, this will be the very last time because this is the last question of the last assignment, last session. So last time, please do answer this poll. the correct option is option C. Hologram records amplitude as well as phase information of the object. So this brings us to the end of the course. This was the last week and we will conclude this course now. Next week there will be one revision session wherein we will just review all the topics that we have learned in these 12 weeks of this course on applied optics. So we will just go through, we will try to cover as many topics as possible and go through some of the assignment questions that we have discussed previously, and some questions which we may have missed earlier. So we will cover those questions in the next session, which would be finally the last session, which is the review session. Officially today is the last session of this course, because this is the last week. Next week there will be just one unofficial, you can say informal review session. So hope all of you have enjoyed this course, and I hope all of you are preparing well for your final exam, and wish you all the best for the final exam, and do score well in the exam. Okay, bye bye. See you next week for the revision.